So this is section 7.1, part 2, an introduction to vectors, and we're now going to look at the algebraic interpretation of vectors. So we're going to look at defining what a position vector is, magnitude, direction, angle, vector, what equal vectors are, vector operations, and algebraic properties of vectors. And some of these topics we've already looked at. The geometric interpretation of them for vectors, like what the magnitude of a vector is, but now we're going to look at actually how to calculate the magnitude of a vector. Okay, so a position vector is a vector whose initial point is at the origin and then the vector terminates somewhere else in the xy plane. Vectors can be thought about as moving, especially, or two-dimensional vectors can be thought about being moved about the xy plane or in Euclidean space. But a position vector is a vector that's initial point is at the origin. So you can move a vector that is somewhere else in the xy plane and think about it being moved so that its initial point is at the origin. So really for any vector, you can determine its position vector. And a position vector is also known as a vector that is in standard position. And you know that a vector is in standard position when you see the vector represented. Now let's say that this vector that starts at the origin and terminates at the point A comma B is named vector V. And we know that vector V is in standard position if it's represented with the pointy brackets and we can see its terminating point A comma B inside those pointy brackets. This is known as component form. Of a vector, and the reason it's referred to as component form is because you can easily see the horizontal and vertical components of the vector. A is referred to as the horizontal component, and B is referred to as the vertical component. Now A just corresponds to the x-coordinate of the terminating point of the vector that's in standard position, and B corresponds to the y-coordinate of that terminating point. But when we see those pointy brackets, we know that the vector that is represented is going to be in standard position. Now, there are other representations or other forms that you can see vectors being represented in, like column matrices or column matrix. Can represent a vector, or there's also I and J form. I and J represent what we call unit vectors. These notations you're going to see in future math classes, so maybe BC calculus or linear algebra, but we're just going to use component form in this class. So like I said, we can find the standard position, so basically the component form of any vector. You can think about just moving that vector into standard position. So this example is asking us, what is the vector in standard position that is equal to the vector with an initial point at 4, 5 and a terminal point at 7, 12. So remember, two vectors are considered to be equal if they have the same magnitude and direction. Let me draw a picture that represents the vector with an initial point at 4, 5 and a terminal point at 7, 12. So this vector is in quadrant 1. Both of those points are in quadrant 1. Just gonna sketch this. Okay, so that initial point and then the terminal point. Here's the point 4, 5, and then here would be the point 7, 12. So for that vector to be in standard position, let's think about how it can get there in terms of translations. Let's focus on the initial point 4, 5. For that point to get to the origin, the vector would need to go to the left 4, or basically we could think about subtracting 4 from the x coordinate of that initial point, and then it would need to go down 5, so we can think about subtracting 5 from the y coordinate of the initial point. And then for the terminal point to follow, we would need to do the same, subtract 4 from the x coordinate and subtract 5 from the y coordinate. So to find the vector in standard position, and I'm going to name this vector v. Vector v in standard position can be found, so the horizontal and vertical components can be found from subtracting 4 from the x coordinate of the terminal point and then subtracting 5 from the y coordinate of the terminating point. So that would give us 3 as the horizontal component and 7 as the vertical component for the vector that would be in standard position. And remember, those pointy brackets indicate that the vector is in standard position. So we've already talked about the geometric interpretation of magnitude of a vector, right? It's the length of the vector. So to calculate the magnitude, which is also known as the norm of the vector, you're basically calculating the distance between 2 points in the xy plane, right? Since we're talking about two-dimensional vector, it would be the distance between 2 points in the xy plane, so in 2 dimensions. So if I go, let's use this vector described in the previous example. So to calculate the magnitude of that vector, which I had named vector v, we would be calculating the distance between the point 4, 5 and the point 7, 12. So that would be the change in the x coordinate squared plus the change in the y coordinate squared, and the square root of that, which would give us the square root of 58. In the previous example, we determined the equal vector that was in standard position to this vector v. So if I draw that vector that was in standard position, which terminates at the point 3, 7, that means that I'm calculating the distance between the origin and that terminating point. So again, right, that's vector v, which is in standard position. You can think about applying the distance formula, or since we're in standard position, this should feel somewhat deja vu. This side would be 3, this side would be 7, and this side would be the magnitude of the vector v. And we have a right triangle here, so thinking Pythagorean theorem, we'd have the magnitude squared equals to 3 squared plus 7 squared, which means the magnitude of v ends up being the square root of a squared plus b squared, or the square root of 58. So if the vector is in standard position, you can just take the square root of a squared plus b squared. If the vector is not in standard position, then you can just think about using the distance formula. So let's find the magnitude of this vector. Since this vector is in standard position, and I know that because of the pointy brackets, I can find the magnitude by taking the square root of a squared plus b squared. So I would get the square root of 26. Okay, so the direction angle of a vector, the positive angle between the x-axis and a position vector is called the direction angle. And I'm going to add between the positive x-axis and a position vector is called the direction angle. So if we had a vector that was in standard position that, let's say, terminated in quadrant 1, let's call this vector u. This would be the magnitude of u, would be the length of the vector, and this angle, which I'll call theta, would be the direction angle. Now, if I were to drop a perpendicular and create a right triangle, you can see that the relationship between the direction angle and the horizontal and vertical components ends up being tangent of theta equals to b over a. So if you're trying to find the direction angle, you could use theta equals to inverse tan of b over a. But you need to remember that the range of inverse tangent is between negative pi over 2 and pi over 2. So I like to call, when I use inverse tan of b over a in order to help me find the direction angle, I like to call this theta star, because if the vector terminates in another quadrant, so in a quadrant other than quadrant 1, I have some extra thinking to do in order to determine that positive angle between the positive x-axis and the vector. Remember, if b over a, so if the ratio that you're taking the inverse tangent of is positive, so greater than 0, that means that inverse tan of b over a will represent an angle from quadrant 1. If b over a is a negative ratio, so less than 0, then inverse tan of b over a represents a negative angle from quadrant 4. So if the vector in standard position that you're trying to determine the direction angle for terminates, let's say, in quadrant 2, okay, so this would be theta. Well, the ratio that you would get, b over a, would be negative, since the horizontal component would be negative. So inverse tan of b over a would actually end up giving you a negative angle. So you would want to add pi, or add 180 degrees to the inverse tan of b over a in order to find that angle, that actual direction angle. If the vector were to terminate in quadrant 3, okay, so that's the positive angle between the positive x-axis and the position vector. Okay, b over a in that case would be positive, because both a and b would be negative. So the ratio would be positive. So inverse tan of b over a would give us a positive angle from quadrant 1. The thing is, that wouldn't give us the angle in quadrant 3, so we would need to add 180 degrees. And then if your vector were in quadrant 4, okay, so that's your direction angle. Inverse tan of b over a would give you a negative angle, and you would end up needing to add 360 degrees to get the actual positive angle, which would be coterminal to inverse tan of b over a in that case. So my point is, if the vector terminates in a quadrant other than quadrant 1, there's some extra thinking that you need to do in order to determine the actual direction angle. So let's look at this example. And I always like to draw a picture to make sure that I'm calculating the correct direction angle. So the vector u that's in standard position and terminates at the point 3, -4, that means that vector u will lie in quadrant 4. So I want to find the direction angle theta. Since the vector terminates in quadrant 4, I know that the inverse tan of -4/3 is actually going to represent this angle, this negative angle. I'll call that theta star, would be inverse tan of -4/3. To find the actual direction angle, theta is going to be inverse tan of -4/3 plus 360 degrees, or plus 2 pi. That's going to be the exact value of the direction angle. And if you wanted the approximation, you could type that into your calculator. I'm going to use degrees. Often with vectors, we use degrees. So inverse tan of -4/3 plus 360 gives us approximately 306.870 degrees. So that would be the approximation. So the exact angle, direction angle, and then the decimal approximation. We talked about how we knew or how two vectors could be equal to each other if they have the same magnitude in the same direction. Well, that means that if two vectors are in standard position and they're equal to each other, they have to have the same horizontal components, meaning A must be equal to C, and they would have to have the same vertical components, meaning B would have to equal to D. They would have to terminate in the same place. Okay, vector addition. We talked about the geometric interpretation of vector addition. And vector addition is actually when you have two vectors that are in standard position. It's really easy. You just add their horizontal components and add their vertical components. And I want to show you geometrically why that works. And I'm going to use the tail to tip method to demonstrate that for adding two vectors. So let's say that we have vector u. Okay, we'll call that vector u. And vector u has horizontal component A and vertical component B. And vector v, let's make vector v like that. Okay, so if this is vector v has horizontal component C and vertical component D. Okay, we have a right triangle here and a right triangle here. The resultant vector, so the vector that is created from adding those two vectors, would be the vector u plus v, and using tail to tip method, this would be the vector u plus v. Now let's look at what the horizontal component and the vertical component of the vector u plus v would be. Now, from here to here is a length of A. And from here to here would be a length of C. Meaning, for the vector u plus v, the horizontal component would be a length of A plus B. And the vertical component, this would be a length of D. this would be a length of B. So the vertical component for the vector u plus v would be b plus d. So if you have two vectors that are in standard position, remember for any vector you can determine the vector in standard position. And if you're trying to add the two vectors, you just add their horizontal and vertical components then. Okay, so these two vectors are in standard position. We want to find the resultant vector, u plus v. And we can do that from adding their horizontal components and adding their vertical components. So the resultant vector would be -4, -2. So the resultant vector would terminate at the point -4, -2. It might be interesting to actually look at this graphically. I use a grid here. Okay, so 1, 2, this would be vector u. And -5, -4. Would be vector v. And the resultant vector would be -4, -2. So in blue, I have the resultant vector u plus v. Now, when we have our vectors in standard position, their tails are at the same point. So if we thought about parallelogram method for adding two vectors, so if we were to construct a parallelogram here, we can see where the vector u plus v, although that side didn't end up so well, the vector u plus v would be that diagonal of the parallelogram. Okay, scalar multiplication. So remember, a scalar is just a real number, and if we multiply a vector by a scalar, if you know the vector in standard position, you can just multiply the horizontal and vertical component by that scalar. If the absolute value of the scalar is greater than 1, it's going to end up increasing the length of the vector. If the absolute value of the scalar is less than 1, so like 1/2, it would end up decreasing the length of the vector. And if the scalar is negative, so less than 0, then it's going to actually change the direction of the vector. So a zero vector is a vector in any direction that has a magnitude equal to 0. So basically, a zero vector can be thought of as like a point. Okay, and vectors have some algebraic properties that are similar to those of real numbers. Like vectors have a commutative property of addition. Okay, an associative property of addition. An associative property of multiplication. A distributive property. Okay, and K still represents a scalar. We have the distributive property demonstrated again. This would be the zero factor law. Okay, the identity property of multiplication. And then also an additive inverse property. And this basically, we actually used this before. This basically says if you multiply a vector by -1, it's going to be the vector that points in the opposite direction. So it takes the opposite of the vector. Okay, so we've already talked a little bit about horizontal and vertical components of a vector. So a vector that's in standard position, and you know that from the, if you're given a vector and you see those pointy brackets, you know that it's in standard position, meaning the initial point of the vector is at the origin, and that a comma b is going to be where the vector terminates. So let's draw another picture of a vector that is in standard position. I'm just going to draw a vector in quadrant 1. Okay, so the vector would terminate at a comma b. The magnitude of the vector u would be the length of the vector. The horizontal component is a, and the vertical component is b. The direction angle is theta. It's easier to see in quadrant 1 the relationship between theta A and B and the magnitude, because we can see that a right triangle can be constructed. So cosine of theta, we can state these different relationships. So cosine of theta is equal to a over the magnitude of u, and sine of theta is equal to b over the magnitude of u. Well, if we solve for a and b there, a ends up being equal to the magnitude of cosine theta, and b ends up being equal to the magnitude of u times sine theta. So we can actually rewrite the vector in component form a comma b like so. And in this form, we are easily able to see the magnitude of the vector as well as its direction angle. Now let's say we wanted to find the horizontal and vertical components of a vector just given the magnitude of the vector as well as its direction angle. Well, if we take the magnitude times cosine of the direction angle, comma, the magnitude times sine of the direction angle. Since 75 degrees is not an angle in the unit circle, you would have to use an identity to simplify that, or we could just leave as is, right? 3 times cosine of 75 degrees is the exact value of A. 3 times sine of 75 degrees would be the exact value of B, or the exact value of the vertical component. If we had another example, like let's say that the vector has a magnitude equal to 7 and a direction angle equal to 150 degrees. Okay, then we could come up with the horizontal and vertical components of that vector. 7 cosine of 150 degrees, comma 7 sine of 150 degrees. And we could simplify. So cosine of 150 degrees would be negative root 3 over 2. And sine of 150 degrees would be 1/2. So vector V's horizontal component simplified would be negative 7 root 3 over 2, comma 7/2. So any vector that has a magnitude equal to 1 is a unit vector. So if V is a non-zero vector, then its unit vector is going to be the vector V times 1 over its magnitude. So if we think about this, which makes sense, this would be equal to 1 over the magnitude of V times the magnitude of V times cosine theta, comma, the magnitude of V times sine theta. Where since 1 over the magnitude of V is a scalar, whenever you distribute that into the horizontal and the vertical components, then the magnitude of V would end up canceling to be 1. So that would give you the unit vector. And the unit vector has the same direction as the vector V. Okay, so to find the unit vector for the vector V, which terminates, it looks like, at 5, negative 12, we need to first find the magnitude of vector V. Would be the square root of 5 squared plus negative 12 squared which would equal to 13. So the unit vector, which I'll call U, I would find from doing 1 over 13 times the vector V, which would be 5/13 as the horizontal component for the unit vector and negative 12/13 as the vertical component. So that's the vector that points in the same direction as the vector V, but has a magnitude of 1. Okay, And I'm going to stop here, and then in the third part of section